Good, thank you. Good afternoon. My name is Shibin Wang, and Mr. Kuir, my supervisor. We come from University of Kassel, Germany. And today I will give a talk about my work, simulation of quasicrystalline fractal behavior with finite element method. This quasicrystal is a relatively new material, so I will give you a brief introduction firstly, and because of the new introduced degree of freedom, the conventional elasticity theory will be generalized for quasicrystal, and based on it we analytically derived some crack quantities to describe the crack behavior. And then we implement it into numerical environment, and by using some numerical method to calculate the fractal quantities. And finally, we do some simulation of crack growth under mixed mode loading, and that's finally the summary. We know that the X-ray diffraction can tell us the crystal structure, and the electron particle do the same things. At 1982, the Dr. Schechtman fired a beam of electrons at a slice of rapid cooled alloy, and in order to understand its crystal structures, and he gets this picture. We can see that this so-called bracket tells us this atomic structure in a certain range is periodic, but that means that's definitely not a amorphous solid like glass, but it shows all the 5 rotational symmetry, which is impossible for the conventional crystals. On the other side, a research group in Numerical, they took an equilibrium structure and mathematically calculated its diffraction, and they found the same pattern in their mathematical result. Okay, that is proof that the experimental result was not a mistake. This structure has a feature that atomic arrangement is not periodic like crystals, but under some certain arranged under some certain rules. Commonly consists of 2 different distances like this. And so people call it quasi-periodic crystals, or just for simple quasi-crystals. And Dr. Schechtman received his Nobel Prize at 1911. At this site, many research groups try to produce the quasicrystals on microscopic level, and this is one on about 1 millimeter by an American laboratory. And generally speaking, the quasicrystal is very firm and hard. This is very suitable to the instrument with demanding on firm surface, for example, in clinic or in kitchen, and especially for 3D print the complicated structure for prototype like this exhaust by using the selective laser theory, and commonly being reinforced by glass fiber, but with the quasicrystalline powder, it could also reach a satisfied mechanical strength. The quasicrystal can be categorized into some subclasses. For example, for quasicrystals, we need one vector with 3 components because it's a periodicity and to describe its repeated atom position. But for quasicrystals, because of lack of the translational symmetry, we need extra component. For example, if we need 1, it's X with a perpendicular number, and that means it's one direction is quasi-periodic and plus a periodic plane with it, and so on and so forth. For 3D quasicrystals, all directions are quasi-periodic. So here we need 3 extra components. Mathematically, this vector with much more components can span a hyperspace. We call it the space from X parallel, which we span the physical space, or we call it the Follow space. That's the space which we can see with naked eye and where the solid really is. And the space from X perpendicular, we call it the Phantom space or the mathematical space. Okay, we go into the mechanical part. This table summarizes all the mechanical variables for quasicrystals. The phonon and the phantom field Actually, these two terms are borrowed from condensate physicals, but here in mechanical, we don't have the original meaning. Of course, the phonon space, that is where we can see the position vector only in the phonon field, and the phonon displacement UI is the change of the position, like our conventional elastic field, and the Phison displacement WI, which means actually a rearrangement. We can imagine it for a phonon string that is normally displacement. If we put this one-dimensional particle that is a one-dimensional sequence, if we push these two in, it changes the position and here maybe shorter. And if we only apply a Phison string, which is impossible because these two terms are associated with each other, and we see that the length doesn't change, but the sequence is changed. So we call it the Phison fleets. So because these two indices are come from different space, so the Phison string doesn't have the symmetry property like the Phison, and so on for the Phison strings, so on for the Phison stress tensor. And of course, the Phison stress is not real, so we cannot apply it as a normal loading. This Phison field has also contributed on the free energy, and this is another definition that the Phison displacement is not linear, but as a diffusive part. But in this work, we take only the linear part into account, and we can derive the material constant and the constitutive equation from the thermodynamic energy, and with differentiation with different state variables. We have the material constant, for example, the C, K are the phonon and the Phison elastic tensor, and R is the coupling tensor. Especially this R is not major symmetry because this WIG, the Phison string, is not symmetry. The IG, the indices are not exchangeable. Okay. The phonon field and the Phison field we can also derive this the stress intensity factors. The anisotropic behavior has an identical formulation. These first three, the K2, 1, 3 with the parallel, are the well-known stress intensity factors, and K with particular is for the Phison string. Of course, that is not associated with any opening bolt, but we write here with these indices to indicate which direction are positively. And for compact notation, we write them together, and this uppercase index comprises all the fractal quantities. We have several equations here, but I will not go to all the details into them. And we can write the closed forms solution in the Schroff organisms based on the polar coordination at practic, and this B, S, and also here A are the characteristic matrices which only depend on the material constant. Important is here we have the relationship between the crack opening displacement and the K factors, so we can calculate the K factors from this UI. Analogous to the Erwin crack closure integral, we can also see that the energy from the energy term can be performed as phonon energy as well as Phison energy for at the cracked ligament with the jump of displacement at the cracked surfaces with a visual crack opening process, and we can insert the negative sphere solution into this integral, and we can get this relationship: the first energy release rate term and the second energy release term. And also the H-M tensor with the energetic observation and the J integral are derived, and we see that for the H-M tensor we have the second term for the Phison field, and the JK, the path independent integral, can be integrated under control with these equations, or alternatively, we know that G1, the G vector can be calculated by the airway crack integrate by the G1 equals to G and G2 equals to the minus H through these equations. In this work, we select a criterion of J integrate vector as a criterion to determine the crack deflection angle, and which means the crack grows in these directions which the G vector towards. The numerical implementation starts the weak form for quasicrystals to the equations with the second order element, and here the stiffness, the compact stiffness matrix consists of the phonon stiffness and the phason stiffness, also the coupling stiffness part. A self-defined unit element in finite element are programmed to cover the phonon degree of freedom and the new introduced phason degree of freedom. We compare the numerical, the crack opening displacement as an analytic solution in a Griffith crack, and this x-axis starts from the crack tip. We see that the plus number is a discrete output of nodes on the crack surfaces are cohesive with the right line. That is a analytic solution very well. And here, because we choose one-dimensional quasicrystal, so we only have one phason degree of freedom, so the indices for W is omitted. As the poster process, we choose two methods. One is the corrective element method to calculate the K factor, where the middle nodes are shoved in the direction of crack tip, and such elements are around the crack tip. And from the K factor, we can derive the G and H, which leads us to the crack deflection angle. Or by another method, we program the path-independent integrate along this right line, where the inner radius is called 0, and we have calculated these two methods in a Griffith crack, where various analytic solutions available. So we see that the numerical result is very cohesive with an analytic solution. Here have to be noticed the error value, the coupling constant, is not a real reliable value, because the research from Japan and French calculated based on some crystallographic method, because they don't have the quasicrystal really big enough to do the experiment and measure the material constant. So that is more or less a hypothetic value, and that's very small, only about smaller than 1% of elastic constant. So we enlarge them by 80 times to see what could happen by a very strong coupling effect. And at least here we see that this shows also a proper result. Okay, now we have the analytic solution, the relationship, and also the numerical method to do some research and this assimilation. And here is a double cantilever beam specimen. We simulated in this geometry with two different single node force, one is 100, one is 99, with the adaptive remeshing algorithm. Why we want to simulate it by these two different single node values? It's built a male design mode with a very tiny shell mode. We know that, as mentioned, R value is very small, so by the very weak coupling effect, we cannot see any strong impact on the, for example, on the pure tensile mode. But we know that for this combination, it's a male tensile mode with a small shell mode. As after several increments, this small shell mode can also induce some decidedly influence. So from this diagram, we can see that at the first, this red line, this R is the reference value. It shows a very great rise. And by the enlarged R coupling effect 50 times and by 80 times, we see that it has actually a negative effect on the crack deflection. Actually, in the simulation for anisotropic material, we have another problem that we need such error matrix B and P as a characteristic matrix to calculate G and H, the energy release rate. But as I said, these matrices are relevant to depend only on the material constant, and this, of course, that will be changed if in the local coordinate system are corrected during the crack growth from the global coordinate. The problem is how can we transform them into this local coordinate system. We found them and also prove that by the error matrix it is not a second order tensor like a stress, but however it can be transformed in the same way. And for B matrix is only one rotation matrix, and the P arcless component for B matrix will be transformed in this way. Okay. This is another specimen we did the simulation. This is only the tensile mode, and here's a hole which also induced a very small shell mode in this region. We see that in this diagram, the right line, the reference R is a reference, R value is still the same, the largest diffraction, and the enlarged coupling effect has a negative effect. Okay, summary. We have do some analytic work to derive all the relationship to calculate the fractal quantities, and also develop the numerical tools to do the simulation. And finally, we do the simulation to find that the small, very small coupling effect, which we cannot see much effect, but a strong coupling effect that reduce the crack path deflection. Okay, thank you for your time.